Hey, in this video we're going to look at Coulomb's law through the lens of the interactive or concept builder that was posted in our materials for this week that we could look at. The Coulomb's law concept builder looks like this on the level 3 one, and in this interactive we're asked to think about how changing the amount of charge or the distance between two charged objects is going to affect the overall electrostatic force. So I have my trusty Coulomb's law written down. Fe, the force of electrostatic attraction or repulsion. That force is equal to Coulomb's constant K times Q1, the amount of charge on one object, multiplied to the amount of charge of the other object, divided by R squared, divided by the distance between them squared. We take our first example. We've got two objects, 1 and 2, attract each other with an electrostatic force of 18 units. If the charge of object 1 is 1/4 the original value, and the charge of object 2 is tripled, and the separating distance between the two objects is halved, the new electrostatic force will be how many units? So we have an old electrostatic force value of 18. We're wondering if we change this stuff, what's going to happen to the electrostatic force after we make those changes? That's our question. So we say the first one here, I'll call it my electrostatic force old. The old one is the one we're starting with. It's K times Q1, Q2 over R squared, and that's equal to the 18 units of electrostatic force. We're going to have a new electrostatic force, Fe new, as a result of changing some of these values. K is still K. That's just a constant. It hasn't changed. Q1, what happened to the first amount of charge? Object 1 is 1/4 the original value. Okay, so I know I'm going to have 1/4 of Q1. That's the change that's been made. We go back, we look at object 2. Its charge has tripled. Object 2's charge has tripled. So Q2 is going to be now 3 times the original Q2. And we're going to divide this by the separating distance squared. We got to remember the squared. And our separating distance, what happened to it? The distance separating objects 1 and 2 is halved. So it's cut in half. So how do I represent that? I have my R, and it's cut in half. So it's divided by 2. Or I could write that as 1/2 times R, either way. But I got to make sure all of that is squared. The separating distance is being squared. So with those changes, we want to see what the new electric force is when the old one was 18 units. So we take a look. Our new electrostatic force is still going to have K in there, right? I'm still going to have Q1, Q2, and R. They're still involved, but I want to look at these particular coefficients, right? The 1/4, the 3, and the 1/2, and see how that changes things. I'm going to write this one more time, but I'm going to pull out my coefficients. So 1/4, I'm going to pull that to the left, the top of my fraction. I have a 3, and then I also have my Q1 times Q2. These are all being multiplied, so I can just rearrange them. And then downstairs, let me look at my exponent there. I want to distribute that exponent first. It's always the tricky part. Make sure we remember to do that. So 1/2 squared is 1/4. And then R squared is just R squared. So we notice we have the same things in our old 18 units amount of force, K, Q1, Q2 over R squared. There's my K, my Q1, then my Q2 over R squared. And now we're just looking at our coefficients. Those are going to show us how the total amount of force has changed. So let's pull out those coefficients a little further, clean them up, and combine them into one number. So I've got 1/4 times 3 upstairs, which is 3/4. Downstairs, I still have 1/4. And then all of that's being multiplied by the rest of the stuff we have in green, my K, my Q's, and R squared. So here's K times Q1 times Q2 over R squared. Right here, this is our original, or what I called the old electric force, which was 18 units. That's what's in parentheses. And then our coefficients that we brought out to the front are telling us how that original or old electric force will be changed once we make those changes to the charges and the distance. So I got 3/4 divided by 1/4 is the same thing as 3/4 times 4/1 multiplied by our Fe old, which equals 18 units. That's all this is. Okay, so 3/4 times 4, what's that going to be? My 4s are gone. I got 3. So the new electric force, Fe new, is going to be 3 times our old electric force, or original electric force, which was 18 units. So it's going to do 3 times 18. So my new electric force is 3 times 18, which is 30 plus 24. So that's going to be 54 units, right? 36 and 18, 30, 40, 54, yeah. Okay, so there we have our comparison. Let's see if we go into our answer box. If we put in 50, 54, there it is, okay, enter. 54 units from the 18, and we have data away. We did it. All right. This Coulomb's law interactive is good for what we call the factor change problems, thinking about how changing certain things, like the charge and the distance between these objects, in the case of our Coulomb's law interactive, how changing those things affects the total amount of force. Good way to look at it, I think, is to draw in those coefficients. In this particular example, 1/4, 3, and 1/2. And then pulling those coefficients out to the front to see how it overall affects the new charge.